So welcome everybody. So today, what I wanted to do today is to go over a reinforcement learning environment that is, it was released by Google Research. It's called Google Research Football. It's a soccer environment. I like this environment for a number of reasons. I think one of the best things of this environment is that it's a multi-agent environment, but you can actually customize it. You can customize the backend so that the reinforcement learning portion of it, the agent actually perceives everything as a single agent. So it's a good introduction to a variety of types of environments, and I think it's a pretty good one to talk about today. So you probably know that I pushed a Docker image in a GitHub repository. So if you haven't gotten that, go ahead and get it, because we're going to be going over that code, and it's much better if you actually pull it and follow along. So let me show you real quick where to get the code. So all right, so the repository is in this address. So you can see here so this is my GitHub account. So gfootball-rlib-intro. So go ahead and pull that repository and then try to follow these instructions over here. I think the most important instruction there is that you want to do the Docker pull of the image, because if you don't do that, I mean, it may take you some time. So you don't want to be waiting on that too much. So go ahead and do that right now. It's probably going to take a little while to go over the entire thing. All right, let me see. So go ahead and try to pull that image. When you pull that image, try to open the image like so. You can see here, so this is, for instance, I cloned the repository here. And then so from the top, from the root of that project, I'm going to run an NVIDIA Docker command such as this one. It's slightly different. You can see it on the left here. This is the one that I'm currently running. And I just want to let you know what's in here. So here, first you clone the repo. That's pretty obvious, right? So clone depth1. This just basically tells me, don't give me the whole history. I just want the most recent code. So, sometimes people checking stuff. And this one is a brand new project, so I don't think you have any problem with that. The first thing to do is to pull that image. Once you have that image, now you're going to run that image like so. This port over here is going to be the Jupyter Notebook port. This port over here is going to be the TensorBoard port. And this port over here is going to be the rlib, well, more accurately, is going to be the Ray port. And then this is going to basically map the directory notebooks from your host machine into your Docker container, okay? And actually this, I believe this command, actually Laha gave me this command, if I remember correctly, for the Windows side. So just do that, the same thing. The only difference is going to be the CD as opposed to PWD. And just a disclaimer that I'm using NVIDIA Docker, which basically passes through or allows Docker containers to use basically the GPU. So all of the information, just the GPU. I guess that's the straightforward way to explain that one. So what you're going to be able to do is then train. If you have a GPU, you're going to be able to train inside of a Docker container using the GPUs that your server, your workstation has. So other than that, these are the URLs that you're going to have to open. I already did. I have them right here. So let me kill this terminal window. So this is the Ray dashboard. This is the TensorBoard, and I think I clear this stuff. Yeah, okay. So this is the thing I was testing the code, and this is the Jupyter Notebook. Okay, and one of the things that you're going to have to do is once you open the Docker, the Jupyter notebook, it's going to ask you for a password. Do RLDM, and sorry for the password. I read somewhere that is important to do that, and so I did. That's it. All right, and then here we are with the code. All right, so didn't know about the NVIDIA Docker? Yes, absolutely. Anyone else have tried this on Windows? I think Laha actually has done it on Windows. So, and I think Laha is actually watching the stream. So if you know, yes, I did. Yeah, I think you gave me those commands. So, all right, cool. All right, so one quick thing, obviously, this stream is to let you know also that Grokking Deep Reinforcement Learning, the book that I wrote, almost 500 pages, well, actually 450, around that, has been released. I do like the paperback, although honestly, you don't see the amount of time that I spent tweaking the figures and making, putting the colors and stuff like that. Well, I have somebody help me, of course, but I actually paid that on my own because I wanted to have a really high quality book. Now, the printed version is not color, so, I think the two sides, I recommend you basically, try to enjoy the two sides, and I think you're going to like it. So it's released. It's going to be available on Amazon November the 10th, I think. So next week. And I'm pretty excited. I think this book does a really good job at introducing the concepts. Okay, so reinforcement learning is this machine learning technique that lots of folks are using. Lots of really big companies such as Google DeepMind or OpenAI and other companies too. Many other companies are using to basically automatically learn behaviors. Okay, I think the major challenge with reinforcement learning in general is that for a newcomer, it's really hard to get in because there are so many kind of I'm gonna call it lingo. There are so many words that if you don't know what they mean, you just lost. You try to read a paper, right, and start reading from the top, and you're gonna get thrown a lot of words, and you're gonna probably understand 10% of the paper. So what this book does is a ramping up of all of those concepts, all the way from the very beginning, from scratch, all the way through, so that when you finish this book, my goal, and I think I did a good job at that, my goal is that you finish the book front to back, the entire book, and then you're able to grab a research paper and you go, understand all of that stuff. And I think I accomplished that. I really, I'm very satisfied. I wish I could spend more time on the advanced topics, such as, multi-agent or model-based and, cool topics that are important. But then I thought, this field is so challenging that if I don't start with the basics, then, most people are not going to get the advanced stuff. And I think that the advanced stuff, I think after you finish this book, you're going to be able to get the advanced stuff a little bit better, as opposed to me just writing about the advanced stuff and just plopping code and saying like, here, have fun. This is how you do it. This is the code, but not being able to actually explain it in a way that you can understand it. So the grokking part is, I think, is accomplished in this book. So I recommend that. That's one thing before we begin. The second thing that I wanted to mention is, so I suggest that you follow me on Twitter. My handle is MIMORALEA, in case that you don't have it there. I'm gonna type it very quickly. So just look, oh well, I guess, yeah, this is my handle. And you can see that's my handle basically everywhere. So, even Stack Overflow, whatever it is. But I recommend you follow me on Twitter. As you can see, I pimped out my desk, my area, And I'm planning to start recording some videos and posting on YouTube. So I'm going to announce those videos. I'm obviously going to be using Twitter to announce those things, but I'm planning to kind of go through some of these, well, I guess a variety of videos, but one of them is try to explain the same concepts that I explained in the book, but in a video format, and perhaps have sessions in which I answer questions, and hopefully, I found a way to bring you guys into the live stream so that the questions can be asked live. I like the live interaction a lot, so I think it adds to the stream. And also, Q&A sessions, and also like deep dives into the papers. I also have interviews with, I work at Georgia Tech as well, so I have a couple of jobs, and then I was writing the book. But one of my jobs is an instructional associate at Georgia Tech. Very happy with that role. And one of the things that I do there is I bring a special guest, and then I do an office hours with them and an interview, basically. Actually, in a couple of weeks, I'm going to have a new guest. I'll be announcing that on Twitter in a week or so. But if you go to my YouTube channel, and I call that channel right now the Agent Whisperer. It's even hard for me to pronounce. I don't know why I put that name, but anyway, just go look it up. You already can see interviews with, Rich Sutton, with Leslie Cabwin, with Michael Littman, with Joshua Kim. I mean, there's a lot of sessions there already. But in addition to that, I'm gonna be continue to do that. But I'm also gonna be adding instructional videos and deep dives into papers and things like that. So make sure to go over there, subscribe to the YouTube channel. Do the little bell or whatever, so that when I start releasing the content, which I plan to release by December, you can actually start getting that content. I mean, this version is good, it's live, but when I do those, I'm probably just gonna edit and try to give you content that is more, boom, here it is. I'm gonna explain to you Markov decision processes and nothing else, boom, and so on. So that is it. Well, the second is the Twitter. The third is the YouTube channel. So with that out of the way, let's get started with this. All right. So let's see. How do I do this thing? Here. Boom. Okay. Yeah. So reinforcement learning is. Oh well. Let me see if there are any questions or anything. Already went through the 50 pages. Awesome. Explains the main concept. Very, very outstanding. That's your YouTube. Yeah, it's hard to pronounce, but it's the Agent Whisperer. Gosh, I asked my wife, like, what name should I put? And yeah, she's like that. And I don't know how to pronounce that thing. Well, anyway, but I'll learn. No problem. All right. So, okay, back to this. Reinforcement learning is a pretty cool field, okay? Now, unlike, I'm gonna say, let's see, most people are used to like the traditional fields of supervised learning, right? In which you have a data and then you basically process the data and do some things with it. And then you go ahead and, train a model on that particular data. And reinforcement learning, some people think that the data is perhaps the environment and the supervision is the reward. And it seems to be, one way, but I don't really like it when people do that kind of stuff. I want to, so if you get to work in reinforcement learning, get a job in reinforcement learning, the majority, unless you are, you're going through a PhD and you're going to be a research scientist, research scientists, let me actually get a little whiteboard or blackboard, whatever this is, yes. So a research scientist would actually work on getting the agents part of the reinforcement learning pipeline, down. But in reality, there are many components there that I want to show you. So one will be the agent, right? So I'm going to call here the agent. Another thing in reinforcement learning, and you're probably familiar, hopefully you are, environment. Okay, that's the second layer. But there's another layer over here. And in fact, there might be actually 2 layers, but I'm not gonna complicate it. I'm just gonna stop right here. I'm gonna say this one is a simulator. Or, I can also call this the real world, right? And usually, or a lot of the work, if you're an engineer, I don't know what your background is, it's gonna be here. It's gonna be in the environment. Because a research scientist is gonna work here, and those guys that are really good at math and at research are pretty good at that. If you're an engineer, you're gonna fall into this place, into this guy over here. Or of course, or the simulator portion over here. But usually the simulator already exists. So there's a lot of work usually done in the integration of, hey, I have a simulator that can make, that airplanes can fly. And it's a flight simulator, obviously, right? Or a simulator such as, Atari. Atari is a good example, right? So the Atari environment is actually a Stella. It's called it's an emulator. So that's actually just like an Atari emulator that you can play in the computer. And then the environment is basically making that, grabbing information from that emulator and passing it through to the agent, right? So in reality, the agent doesn't talk to the simulation. The agent actually talks to the environment, okay? So I think that distinction is often overlooked, and is something that is important to be aware of, okay? So the one thing is, or one of the things is that there are often lots of simulators out there. And you can actually go ahead and look it up. I mean, I'm not even kidding you. If you look for gym environments, usually just go, like this, gym environment, and then, search for, flight simulator. You're gonna find reinforcement learning environments that have a simulator on the back end, okay? In the particular case of the project that we're gonna be working on today, that is basically you can see in that paper, is like a little, looks like a game, like a video game, right? So, I mean, who has played soccer video games in the past? That's what it is, right? So this guy is actually the backend. This is what we call the simulator. This is not the environment. And you can create from a simulator like this one, you can create many different environments, okay? The kind of cool thing that Google Research did by releasing this is that they hook up this simulator with soccer and then gave you the ability to create many different environments that you can think of, okay? The environment, and let me go back then to the whiteboard thing. Usually when, so the communication here is like this guy, oh, that's not what I intended to do. Let's see that, okay. So this guy talks to this guy talks to this guy, then this guy to this guy to this guy. So usually it's like that. The communication goes like that. One information goes from one place to another. Well, from the agent to the environment, there's an action being passed in. And the action can be, discrete, can be continuous, can be a vector. So you can pass an action that is a 0, or 0 to 10. That is a single integer, right? It's a single value that can, carry different values, can be from 0 to 10. You can also have a vector, right? That, 0.314, comma, whatever, right? So the action can be anything that you want. It can be a combination, of course, and if you can obviously make one of those a kind of float with a threshold to make it a discrete value. So if let's say that, in your simulator right here, let's say that you have an airplane, a fighter, a jet that fires a missile. If the fire action is not continuous, you don't need to, it's 0.1. What is that? It's a button, right? You push the button and the thing goes out. So you can train the agent with a threshold, right? So that you say, hey, once this value is greater than 0.9, then that's it. All right, but without getting into those specifics, the actions come into the environment, and something happens in the environment. So there's some processing going on in the environment. Okay, something goes. Usually that processing means you're going to apply actions to the simulator depending on the information that is in here, right? The environment, some people say like, oh, the environment is kind of like an adversary to the agent. No, don't think about it like that. It's not like the agent against the environment, and the agent tries to get points and the environment tries to not let the agent get points. That's not the way reinforcement learning is. Although, of course, you can create such an environment. That's not a good definition, a general definition of the environment. So if you develop this portion over here, you can do whatever you want with it, okay? You get that information of the action. You go out and process, try to what we call step the simulation, right? You apply the actions, then step the simulation, then query the simulation to get the state. So this basically in here, what comes out of the simulation, we can call it state. Obviously, simulation can have partially observable information, but most of the time what we get from the simulation is the state. Then the environment processes that state and then outputs something to the agent. It returns to the agent an observation, which is basically a filtered version of the state or a processed version of the state, or it could be equal to the state. And I mentioned this in my book, but lots of folks actually mix those two, and it's not bad intention. It's just the way it is. But just know that when somebody says observation, they mean that there is likely that there is some information that is partially observable, is not fully observable. The agent doesn't know the true location of the airplane. The agent knows a sensor view of the location of the airplane, which contains noise and all that stuff. So you get an observation, the other thing you get is a reward. And this is a little challenging, but we'll talk about that a little bit in a minute. And then, usually not mentioned because they're used in a different way, the done and the info stuff. Now, what I'm describing here is what OpenAI came up with. So when you hear OpenAI Gym, what people are referring to is twofold. One is a collection of packages that bring a lot of different environments. And I mean a lot of different environments, such as, all this implementation, basically, okay? So that is one thing. The second thing that they did, the good contribution, is an interface. And the interface is basically a few functions. Actually, it's just, the step function that takes in an action and returns these guys, okay? The second thing is a reset function, which doesn't take anything, but it returns an observation. And then so the reset is going to become like the entry point of an episode. So if you think about it as an episode, is when we can call it a trial, right? When the agent is going to start trying something from zero. It's like the beginning of a game of chess. That's you reset the environment and it goes back to that initial position. And then you start stepping through the environment, passing actions to the agent. So in reality, the very first thing that the agent gets is not a reward. It's an initial state, is the state. So this observation is what the agent gets to begin with, okay? And then the other thing that, is a render function, there function. And and a close and so on. So a couple of other kind of helper functions for the environment. But they came up with this interface, and lots of folks now can implement this interface basically. And the awesome thing is that you can now leverage, right, lots of implementations of agents. Because if you have that interface here, if you create all that is in here, you can plug in any agent basically whatsoever that you need, that you want. Okay. So let's see. Seems to have an issue. It's working on Windows 10. Let's see. Repo, try this. No, this one. The repos should be very similar. So, looking at the mail yesterday. Excellent, outstanding, super happy for that. Yeah, so if the repos of GDRL and this one are almost identical, but I added some, I added the soccer environment so that you guys can test it out. And I also added RLib so that you guys can train agents using against this environment. So I think that is a good contribution so that you guys don't have to mess with that, and you can see the helper functions that I created. I mean, I'll be honest with you guys, it's not perfect. I worked on it today. So, but it should actually work and kind of help you, go forward. I know this stream may take a little longer than I thought. It's not just an hour. I think it's going to go a little bit over, but, it gets recorded. So if you guys, have to go to bed or whatever, feel free and then you can continue watching. But anyway, so, all right. So this is the situation. Okay, what we're going to be talking about today is we're going to be using RLib for this portion over here, okay? In my book, my book concentrates on reinforcement learning agents and kind of explaining to you what is reinforcement learning first from the perspective of the environment, and then starting in chapter 3 on basically from the perspective of the agent. What's happening really in there. In reality, and I do give you a lot of pretty, I'm going to say, what is the word? Implementations that I hope help you understand the agent side of things, okay? Now, would I use that implementation for a project such as the soccer environment here? Probably not, especially because this environment now there's a competition going on. And by the way, you guys should share that in the chat. So there, I think it's Manchester City or some soccer team actually is, how do you call it, sponsoring a competition and, do well in this environment. So, but, I'm going to teach kind of like the very basics. So to get you up to speed with RLib in this environment, I'm not going to teach you all the way to multi-agent and all the tricks and techniques, but, you can continue. So even though I have those implementations in here, I probably would not use it for this. And that's the reason why I install RLib, Ray, and all that machinery to try to explain to you how I would do it to compete against the big boys, okay? If you want to do it, you're going to do your own DQN implementation or even my DQN implementation or the DDPG or the PPO. It doesn't really matter. I think you can get a lot more from RLib, and I tell you some of the reasons why. But the main reason to me is the scalability aspect of it. Okay, my implementation uses a few cores and nothing else, not much, and really slow for training, because all what I wanted to do is kind of output strings so that you can follow along and understand all that stuff. But in reality, if you want to train agents and not necessarily understand the algorithm, but just train the agent, then you need to remove all that overhead and get down to business. What is the fastest way to do multiplication? This, okay, then use that, as opposed to do it the easiest way to or the best way to understand the algorithm, right? So there are two different approaches. Anyway, so we're going to be using RLib for that, and we're going to be using the environment, I actually give you an environment in there that I kind of use, I modify it from online, but they do have a multi-agent wrapper that you can use for RLib. And then the backend is going to be the gfootball environment that they have in there. Okay? All right, let's get started. So far, so good. Let's see. No questions so far? Okay, let's proceed. All right. Let's go back in here. Let's get back to the paper. Okay. Okay, so one of the coolest things is in this, if you go to this link over here, they they give you the simulator, simulator kind of ready to do things. In here, you can actually do multiple things, such as you can control this guy and this guy and this guy and this guy and this guy using multiple agents, multiple policies, that is. Okay, so you have a reinforcement learning. This guy can be, let's say this guy is a DQN. I'm not sure you want to do that. This guy is a PPO. This guy is a whatever. So you can really do whatever you want here. Okay. I'm not saying that multi-agent, that's the best strategy, but you could. So, you have this version of collaboration between your agents. This is a multi-agent problem. It's pretty good. You can also have, you can have that guy over there, right? And then you can have, obviously, the other team. So this guy, this guy, this guy, this guy, those are different agents as well. So now you have collaboration and competition at the same time. So you have a, 11v11 in there. I actually created a few config files so that you can load, and in the simulation, you can actually load a 1v1. So there's going to be only one, it's going to be only one player on one side and one player on the other side. And the other player is going to be a computer. So this is going to be a single agent. What we're going to do today is going to be a single agent training to play soccer. The one thing is, though, I also have in there 1v1, 2v2, 3v3, 4v4, and up to 5v5. Okay, so you can, once you move on from the single agent, I recommend you go to the 2v2 and so on and try to see the complexity, try to deal with that complexity on your own. One thing that I'm going to mention is that I added I added all those five simulation scenarios, and from 2 to 5, I additionally added what I call auto goalkeeper. So if you play soccer ever in video games, you know that the goalkeepers are, pretty, they have their own kind of behavior. Well, in reality, in soccer, every player should have its own behavior. So I challenge you to try the different things and try to perhaps even train these agents to play, I'm going to play a central defender as this guy or a forward as this guy. But, that's, you get advanced. But you have the capability with this, with what they release over here. So from 2 to 5, you have the auto goalkeeper version. So in that case, you will be one agent. 2v2 with auto goalkeeper will be one agent and one computer, so a scripted goalkeeper playing with you. And then that one agent will be playing against two scripted players. I hope that makes sense. And 3v3 would add two agents and then one goalkeeper, and then against three scripted agents, two players and one goalkeeper, but scripted. And then 3v3 auto goalkeeper, and 4v4 auto goalkeeper would be 3, and so on. Okay, so you have the two versions. Go ahead and play with that. All right, so let's get to the notebook. Let's see, how do I do this? I do this like so. Yes, okay, cool. All right, so let's see, just make sure we don't have, can two agents share their observation with each other? Ooh, great question. So yes, and if I'm gonna have to do another stream to go over the actual, like, the multi-agent part of it, because there are techniques that, if you think about it yourself, even soccer players, they go out and train, 5 days a week, and then play during the weekend, right? So why wouldn't you let agents share observation during training, as opposed to all the time? Because usually what you want is decentralized execution of a policy that you learn. What is the best thing that I can do from this position? But during training, many multi-agent techniques are basically based on that, of what they call sharing a shared critic, which, in some extent, you can also do share observations, full observations. You can also do things such as sharing the state of the environment, not just observation, but the full state. Because if you think about it, when you're doing training, you can know everything that you want. You're training, basically. What you care about is your performance during your evaluation phase, your execution of your policy afterward. But if the goal is very well defined, such as in soccer, which is win the match, score more than the other guys, you can do whatever you want. You are open to do whatever you want. So yes, you can share observations. Usually the limitation is when is the execution portion of the whole problem. Then now you have to, we need to talk, be honest to each other. Are the agents really going to be able to share observations or not in that environment? In soccer, they don't share exactly the same field of view, right? But they can communicate. So that's another thing that you add to the whole equation. So that's an excellent question, and I think, hopefully, in the future I can go into more detail on that. All right, so people already have the notebook kind of going, because I am going to get going. All right, let's see. All right, so the first thing here that you're going to see is I do all the imports. There are more imports here that you really need. I just copy and paste a bunch of stuff from another notebook and then start adding and removing it as I see fit. Here, what I'm doing is I'm sending this command to the Docker container and making sure that we have these versions. You would have problems if you don't have TensorBoard 2.3, but because I made the image for you, you should have exactly the same version, unless you build the image separately, as opposed to pulling the image. You build it yourself, then you may get another version if they released the version 2 minutes ago. But yeah, not likely to happen, of course. I'm kidding. So you have here some versions here. If you have a GPU, you run that command and it's going to tell you that, yes, I can see the GPUs. Otherwise, try to make sure that you instead of running Docker, you run NVIDIA Docker so that the GPU shows up in the container. And again, hopefully you understand how this is actually working right now. I have my host machine, and the host machine has has an installation of Docker, a Docker service. It has the drivers of a NVIDIA Docker that allow the GPUs to be shown up in the container. And then I'm starting this container, and then I'm mapping all these ports so that my host machine can access the ports to the container. So that in reality, even though I'm in my host machine, this localhost 88 is actually this notebook is actually being executed inside of the container. So I hope that makes a little bit of sense. Okay, so here is what I mentioned. I created a bunch of different environments. This is the 1v1, the 2v2, 2v2 auto goalkeeper. This will be a single agent environment. Okay, hope it makes sense, this single agent, because it has a one auto goalkeeper and one agent. Okay, so this one would be, I would actually go from here to the 2v2 auto goalkeeper and see how the agent performs there, and then start doing the multi-agent, the 2v2, and then go to the 3v3, and then, you know, the auto goalkeeper and so on. Here you already have, in reality, I should sort this, you know, more like this way. This is actually the level of difficulty that I would recommend for you guys, for anybody, even for myself. I would do exactly so, like that. And you know, all these changes, I'm gonna save them and push them right after this thing. Question, let's see. I'm curious about what the state, or rather observation, would be from an 11-11 game. Would each agent know the exact coordinates of all other 21 agents on the field? Is there a way for the agent to only know the coordinates of other agents within some distance from them? That's a really good question, and we're gonna be flipping to the paper and kind of, you know, discussing those things, which I think are important. I don't know 100% for sure. Like I said, I actually started working on this today. I got excited that recently they released this challenge, and I thought, hey, might as well take a look at it and see. But I think we're gonna answer your question in a minute once we start reading the paper. All right, so this step over here is basically going to create the soccer environment. Here, what I'm doing is I'm running 100 steps. And you can see here, I'm saying, hey, environment, from your action space, sample an action, and then pass it to the step function. So this portion over here is basically what I show you on that tablet. I guess I can do this, is basically, no, this one, iPad, there you go. Is basically doing this communication between this guy over here. This is the action being passed in, and then something's happening here, but I don't care about that because they already did it for me, right? So the Google research folks actually did that for me, and then the environment is going to pass back some stuff for me. Okay. Very cool that they. Let's see that. Okay. Yeah. Okay. So that's what I'm doing here. Here I'm saying environment render an image for me so that I want to be able to see the game, the video game. I grab that image, I put it on a plot, and then I show the plot right there. And this is what we see. This guy, this is the other guy. So if you see my mouse, hopefully you see the little tiny things over there. We are left, the opponent is right. This guy here is a referee, believe it or not. Yes, they added a referee. I don't even know if the referee is in the observations, but I hope not. All right, so the other thing that I'm doing here now is I'm resetting the environment, and well, the reset, like I mentioned before, returns an observation. Once you reset the environment, I'm saying, give me that observation and give me the shape of the observation, mostly because I'm trying to, you know, get this information. And you can see here that there is some, it seems to be an image, okay? And the reason why is because I created the environment here with the default parameters, which let's see, where I can show you that. I can show you here. The tools, is a little package that I created here. The representation here, you can change it. So later we're going to be using a vector as opposed to an image, but I didn't care too much in there. So, okay, so the first cool point, and now let's switch to the paper and then start kind of reading there. All right, so the first interesting point is that we have, let's see, this is the introduction of the stuff. You know, so, okay, so here it is. They talk about the football engine, which is the simulation, what I've been talking about, the simulation, right? And you can do many things in there. Now, what kind of environment can you create? Virtually, if you are a coder, you can create anything you want, okay? You already have the simulation, and simulation is a full soccer simulator that allows you to do penalty kicks, free kicks, and so on, right? So, you know, give you ideas there, all the things that you can do. Open source license, know of the model. All right, so single player, such as Atari control a single player, other football environments, related work. Here it is, state and observations. Opponents, so opponents and AI built-in bots. I was talking that they have auto players, and you can actually customize too. You can actually say, hey, I want to have 2 controllable agents and 3 computer, opponent AI, what they call that, or scripted agents is what I call it, playing in my team, right? So we have 5 players, 3 scripted agents, 2 reinforcement learning agents that are learning, and then you can have the other team doing something else and so on. You can customize it whichever way you want. State and observations, here it is. We define the state as the complete set of data that is returned by the environment after the actions are performed. On the other hand, we define observation or representation, any transformation of the state that is provided as an input to the control algorithms. Great, so this is what I was talking about before, is, you know, you have the state and then you have the observation. Not everybody does this for you, so good job, guys. Let's see. Information. Okay, so the definition of the state contains information such as the ball position and possession, coordinates of all the players, the active players, the game state, the tiredness levels of the players, yellow cards, score, etc. Of the current pixel frame. And the current. Of the current. What do you mean? And the current pixel frame. Great. So you have the state contains all of the information we need. Okay, everything is going to be there. That doesn't mean that your environment is going to have to be passing that information back to the agent. Your environment is going to use the state to create observations that you want. Now, they provide you with a few standard observations, okay? Here they talk about it. So we propose 3 different representations. 2 of them are pixels and SMM, which is super minimap over here. The pixels and then the floats. Those are the 3, okay? So the pixels consists of these images corresponding to the render screen. This includes both the score and blah, 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 blah. The super minimap is actually what I have in here, and that's why you see the size. Let me flip back in here. You can see here the size is 72 by 96, which is basically what they have right here, 72 by 96, right? And it says consists of 4 72 by 96 encoding information about the home team, the away team, the ball, the active player and the active player respectively. The encoding is binary representation, representing whether there is a player or ball in the corresponding coordinate. All right, so let me show you that real quick. So I said this is that. I can do it again here. Okay, so the observation, this one is, let's see, where do I have that? Do I have that? Yeah, there it is. Okay, let's see if I can regenerate that stuff. Okay, so this is the other kind of observation space and the one that we're going to be using, but I'm going to go back to the minimap in just a second. I guess I'm not sharing the screen. Am I sharing the screen? No, I'm not sharing the screen. I gotta get better at that. Okay, so you have the observation there. We do the sample, and look at that. So now we have in the one. So in the last one, I guess I probably gotta talk about that too. So the last one is this one. The floats representation provides a compact encoding and consists of a 115-dimensional vector summarizing many aspects of the game, such as player coordinates, ball possession, and direction, active player, or game mode. Let's see. Okay, so those are the observations. Let's try to look at the observations a little bit on the computer. Following, awesome. Okay, all right, so yeah, now we're looking at are we looking at what? What are we looking at? Okay, cool. Okay, so here I'm creating the float version, okay? And if I, go through this, you can see I have the observation space, which this thing here is telling me, so the observation space describes what the agent can perceive. The agent in this case can perceive 115 float 32 that can go potentially from -infinite to infinite. Now, I challenge that that is not the case. In reality, those values should have a low and a high that are not necessarily that. And, you know, I would argue that, you know, perhaps, you know, I'm sure that information is somewhere in the paper, but, you know, they a little sloppy. They could have just put the min and the max in there that are correct. In the case that are different mins and max, you can do other kinds of observation spaces so that you can have the full information in there. But that's okay. I mean, nobody's gonna, you know, I basically copy some of the code that I have in some example, and you know, that's what came. Okay, so this observation space sample is basically now generating a sample observation. Now, when you do this observation sample, you're not really creating a I'm gonna say a true sample of like the game. It's just gonna be a kind of uniform kind of like a random observation based on the observation space. Okay, but it doesn't mean that this value is often this way. Okay, so don't be misled by that. All right, so in this case, the other cool thing is that the action space is very small. In this case, it's discrete. And if, you know, I sample an action, for instance, could be something like that, right? So if I sample it again, it's at 0, and so on. All right, so the actions are 19 total actions. Let's switch to the iPad real quick. And then, so if we continue here, we can see that the action says, the actions available to an individual agent player are displayed in table 1, which is somewhere in here. Thank you for that. Where's the table 1? All right, so those are the actions. There it is. So the actions are like when you play the Nintendo or whatever, the Nintendo. Oh, I'm showing my age. Sorry about that. Whatever it is that people use now, PlayStation. There you go, or Xbox. You can you have these actions, right? So you're going top left, you're going bottom left, bottom left, and so on. Also, all the directional moves, right? Plus, you do short pass, high pass, long pass, which are these ones over here, right? And then you have the little shot, which is the square. I used to play this a lot. Do nothing, which means you let that frame do nothing. You let the next frame come. You also have the kind of defensive version of these controls. So I'm not sure if, you know, I'm not sure if they could have reduced this and it just like when you are defending, you are using some other version of this. But anyway, this is what they decided. By the way, so let me say it again. You can do whatever you want with it, right? So you have the simulator in the back end. You can customize this to your liking. Okay, I'm not saying that is where I would spend my time, but you could if you wanted. Okay, so let's see. So those are table 1. Okay, they include standard move actions, say directions, and different ways to kick the ball, short, long passes, shooting, high passes that can be easily intercepted along the way, of course. Also, players can sprint, which affects their level of tiredness. That's cool. Try to intercept the ball with a slide tackle or dribble. If they possess the ball, let's see. Okay, so they do that if they possess the ball. We experimented with an action to switch the active player in defense. Otherwise, the player with the ball must be active. Of course, when it's in offense, right? Defense. Okay, so however, we observe that the policy is tending to exploit this action to return control to the built-in AI behavior for non-active players. Oh, I see that. And we decided to remove it from the action sets. We do not implement randomized sticky actions. Instead, once executed, moving and sprinting actions are sticky and continue until the explicit stop action is performed. Stop moving, stop sprint, respectively. Oh, that's interesting. That's cool. Okay. So here, so randomized sticky actions is something that was done in Atari that I suppose is the action repeat, basically. And sometimes like the actions basically repeat for a number of frames, whether you want it or not. But obviously, in this case, that would not be cool because if you probably always, I don't know if you ever play soccer and sometimes you kind of slide and then slide again and then all of a sudden it's a red card for, you know, doing a sticky action and you didn't want to slide twice. You just wanted to slide when the ball was coming and whatever. So it makes sense here. So that's actually good. All right, so that's that. And we're going to go to the rewards in a second, but let's get back to the computer here. Okay, so let's see. All right, so I already showed these two. The next thing we need to do is, and I wanted to show you this so just so that you are aware of it again. Oh, let's see, questions. So do we have continuous and discrete in each action in environment? Do we have continuous and discrete? Action equals continue, discrete. No, so the action is a discrete. So it's a one is a discrete and it's only a single value, right? So and it's gonna be a value. You think about it as a 0, a 1, or a 2, or a 3, or a 4. That's it. And each number is gonna mean something else to the player down the simulator. Does that make sense? Cool. Outstanding. All right. So I wanted you guys to have this hopper environment here because, like, you know, Laha is asking there, you know, it may be disappointing to have an action space that is such as that one. In this one, for instance, there's an environment called the hopper. You can see here, this is a little bit, you know, better prepared action space. You have the minimum value of -1, the maximum value of 1, and then you have 3 floats. 1, 2, 3. And these 3 floats mean something, you know, different. One is gonna control the knee of the hopper, and you know, we can very quickly hopper. Oh, it's hopper environment. No environment. Reinforcement learning. All right, so hopper environment reinforcement learning. In this case, this is the Mujoku one, but is this little funny dude. So you're probably controlling this joint, that joint, and some other thing, right? Or the little motor there. Yeah, this guy. So the one that I'm you can try to train in that one too. But the one that I'm doing is the one that is called bullet, like that. Bullet hopper environment. Bullet. Maybe I don't know. Anyway, it's very similar, and I actually use it in my book in case that you want to. Oh, look at that! That's my book. Okay, cool. Let's go back in there. All right. So, but yeah, I wanted just to let you know that in this case, for instance, the hopper environment has 15 variables for the observation space and 3 for the action space. So, you know, sometimes it would be nice to have all of the actions, right? Because you're like, you know, going up and also making a pass at the same time. And then so, you know, the ability to have all those actions at once may, I don't know, may change stuff, right? So I don't know. But in Atari, they solved that by just basically combining the actions, which I don't think they did that. But stop screen, left, right, maybe not, but that's okay. All right, so, okay, proceed. All right. Okay, so that's a temp environment just to show you that. Now, this is the real stuff. So when I do environment reset here, you can see now an actual array with some values in there. And let me see if I can, they probably have an appendix with all of the variables. If I find it, I'll share. Okay, I don't have it right now, but that's okay. We can, you know, there are ways to find out what each of these values really mean, which, you know, when you start getting serious, I would recommend you do that to see if you really want to pass information. Here you can see there are a lot of -1s, there are a lot of zeros, and only a few, non-1, non-zero variables. What does that mean? Does that mean that we could trim this down to something much, much, much smaller? My guess is yes. I would say yes. There's definitely some way to actually trim down this observation space, but for the time being, we're just going to proceed that way. All right, so here I'm advancing the simulation a little bit, and the reason why I do this is just kind of to try to observe what the environment has, after a few steps of the simulation. And you can see that, for the most part, there's a lot of garbage in there that you could actually trim that observation space to bare minimums. Again, and something that you would have to research. I didn't find it in the paper. We're going to go back to the paper in a second just to talk about the rewards and so on. But I'm sure that is somewhere in the Google research portion of things, right? So if you do Google research, that guy, I'm sure that there somewhere you can actually find how they create the environment and what they're actually passing, here, the observation. Yeah, I wouldn't do that right now because we're already 1 hour and I'm not even halfway there. We got seven folks. People are leaving. Okay, all right, but that's okay. Let's continue, see what we can do here. All right, the reward in this case is 0, the done is false, information, there's some information, and so on. So that's actually interesting. Now what we can do is actually now step through the sample environment for 5 episodes and see what happens, okay? And I do that, and you can see how it's starting to do its thing. Let's see. Yeah. Cool. So here, what I'm doing is, so I start the environment here. I reset the environment, get the new observation. I'm calculating the return, which is the sum of all of the rewards in the episode. And then I set the done flag to false. I run for 5 episodes, and I'm gonna pull 3 videos to look at what's in there. Okay, and you can see here, there's a little progress bar, and here you have the episode 0, return 0, episode 1, return -3, episode 2, -1, and so on. So obviously here, as you can see, I'm basically having a random agent. The agent is really not doing anything interesting, and I don't expect the agent to do well. I just want to show you what it looks like, okay? So in the Docker container, I can pass in this command to actually show the output of the videos that I created, okay? I created a little helper function that allows you to display how those videos look like. And now you can see basically what the agent is really doing in the environment, okay? So now it's processing, is basically, if you have trouble with that function, is because of memory issues. So make sure that you have a workstation, or if you have if you don't have a workstation, then I recommend you go here to the GIF tools and then try to play with this guy, and this guy. Kind of reduce the scale of the video so that you don't run out of memory before. So you know what BitLocker is? No, I don't. I'll look at that later. Let's see. But okay, let me see if I continue here. All right, here you can see there's a G. This is the goalkeeper and the other goalkeeper. It doesn't really matter. They're not, doing anything. That's the ball. You can see how we are the left guy. They have some kind of automatic behavior. So even though it's random, when there's a particular action being pressed, then the agent has wants to basically get close to the ball. All right. So that's why you see the agent going to the ball and then kicking it, and then going to the ball and kicking it, because there's the auto, behavior in there. Yeah, so I printed a couple of trials there, so for you to look at. And then let's see. So here, one other thing that is important to do, and now I'm gonna get into the RLib side of things, is make sure that you have X number of processors, and have that in mind, because we're gonna be using processor, not just the actual CPU, but the number of processors that are available to Linux. The Docker container is a Linux machine, and then there are so many processors that are going to be available, and you're going to use that to train. Okay, in my case, I have 32. It's a pretty beefy processor. I could go all the way here to almost like 30, right? And it would be pretty big, pretty fine. Here I'm going to be training a carpal example. Okay, just to demonstrate what RLib is. In this case, I'm using, so RLib is actually initialized on startup. When you start the Docker container, it's going to come up with RLib and all that stuff. And you can see here, it's going to come up also with TensorBoard, and it's going to come up with the Ray dashboard, so that you can monitor the use of the resources in your machine. Now, this one is not as important. This one is very, very cool and important, and you're going to see what happens. Okay, so first thing we're going to do is we're going to run a PPO agent. You can see here, we're telling it run a carpal environment, use 1 GPU for training, use A workers, and this is going to be like the parallel execution of rollouts. So the 8 workers are going to be sampling their policies and going through some episodes, collecting that data, and then moving that data, centralize it for the trainer to grab batches of data and then churn the data, and improve the policy, and then redistribute the weights so that the workers can use new and improved versions of the policies, and so on. Okay, the episode. So here is the stop criteria that I'm using. I'm saying, hey, when the episode reward mean reaches 150, then stop. Now, if you're not familiar with the carpal environment, which I would be shocked if you're not, I recommend you look in in my book and then come back to this. Is the player rewarded for getting closer to the ball? Yes, and we're gonna go over that in a second. All right, so here the only parameters that I'm changing is the learning rate. I'm saying use that, or tuning that stuff. We go there and we see what happens. It's grabbing 9 processes out of 32 that are available in the machine, 1 GPU out of 2 GPUs available. So you see I can actually use more here. It's grabbing 8 because 9 as opposed to 8, because 8 are for workers and 1 is for the trainer. Okay, you can see here the training happening, and then if you flip to TensorBoard, and sometimes you're gonna have to refresh, you're gonna see stuff coming up. Okay, beautiful. This is actually why I like RLib, because they have all of this built in. You don't have to do this yourself. You train one of these agents, and all of the information shows up in here. You can actually use TensorBoard and just regex syntax in this case. The thing that I want to look at is the reward mean. Okay, so here you see that my agent is learning. It's going up. Boom, 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 boom. This is what we look for. This is what we want. This means that the episode reward, which is the return, the mean return across multiple agents, multiple workers that are rolling out that stuff, so that's why it's the mean, is, at this particular time is 161, and the smooth value is 131. You can see it there, right? So the smooth depends on this guy over here. I can say, hey, you can, I want to use a very, I want to be very quote unquote safe that my value is what the value is saying there, or you can say no, whatever. So here, you know, I don't need to smooth that value. I just want the true value in my graph. Sometimes when you have multiple, when you have a very noisy environment, this can be like super, super noisy up and down, right? So using the smoothing is actually helpful in that sense. All right, so you can see here it's terminated. I ran it for very little. There's not much in here. So this is our lib, what I'm showing you here. Our lib is a reinforcement learning, I'm gonna say framework package that is based on Ray. Ray is pretty good at distributing jobs across multiple. So if you have multiple servers, you can actually do that in a really nice way. Now, the cool thing is that you don't need to have a farm of servers to actually use RLib. As you can see here, I'm not only using Ray and RLib in a Docker container, in a single machine, but also in a Docker container. So it's very, very restricted in this case. However, it is very easy to scale. So for the most part, that is transparent to you. So you can iterate using a local machine. And once you're confident and you're happy with what you have, you basically say, hey, now I'm gonna send to the cloud, to AWS, and train for a few hours, and boom, you know, back you get your thing, right? So this case, we're local again, but I think Ray is really useful for these kinds of projects. So here are some two locations that I would recommend looking into. The temp logs are going to be the training logs, and you can see here the ls command actually returns a carpel folder, mostly because I organize the experiments. So all of the experiments that run with this thing are going to be organized there in the carpel category. Okay, if I have more experiments, I would have many different ones, right? In this location over here. And then the other interesting thing that you may want to look into is the temp Ray session latest and logs. And here you get all the Ray specific logs. And some of these are interesting to look at. You can see here the Python course. So these are the workers. And basically the workers can have information about the environment. Whatever you output in your environment, you may actually get through some of these workers. And so, you know, it's pretty good when you're trying to troubleshoot, you're creating an environment, I recommend you look into these locations. So right now here, I'm basically removing all the logs, the training stuff. So then TensorBoard should just be clear at this point, and it is. And then I move on. All right, so now we're gonna get a little bit more advanced on RLib, and then we're gonna go back to talk about the rewards of the soccer environment, and then we're going to train a soccer agent, okay? So this in here is a little bit more complex. You can see I added a few more stop criteria. I said, hey, I want only 10 training iterations, and this number can vary depending on a variety of things, so I'm not going to get too much into it, but it depends on the number of the size of the rollout, the number of batches that you're collecting for sampling from your replay buffer, and how many stochastic gradient descent iterations you apply every training iteration, and so on. So, you know, I'm not going to get into that detail right now, but what I'm going to say is, you know, this value is perhaps confusing, and, you know, I probably would remove it for for other purposes, but I wanted to show you that you can actually define multiple stopping criteria. The same stopping criteria here of episode reward, 195 rewards, but because we're going to be doing a search, so we're going to try to train an agent that is really good. So the search, then I want to block the agent from going beyond, so any worker, no, sorry, not worker. The entire training should not exceed 50,000 time steps total of experience. That means multiple workers are going to be sampling their experience and so on. The accumulation of all of those should not exceed 50,000 time steps. And then in this case is the accumulation of the episodes should not exceed 500. Okay. You can see here, I'm actually doing the same carpel. This is the carpel environment right there. I'm saying like, hey,
pick a gamma between this and this, and you can see here, this is a sampling that you can do uniform. Now, I'm not doing this because I recommend that you play too much with gamma. I'm only doing this because to give you the information of what you can do with this, okay? And then you can also do the grid search, which is more like you know, fix this value. I want this value to be tested. I want this value to be tested and this value to be tested. Usually the way I do it is that I start with a very wide grid search experiment. And then I run a wide experiment to kind of have a ballpark of what values I should be using. Once you get the ballpark, that's what I normally use. Once I have a ballpark that is, you know, narrow, then I do the kind of tuning with the uniform stuff between this and this value. That's what's, you know, best. So I would do it that way. There are other training techniques such as population-based training and, you know, advanced things, Bayesian stuff. And our lib actually has those things. The scheduler. They have a few different classes, but you can actually just, you know, Google it. Population-based training, our lib, and you're going to get to their documentation page. You could try to implement that in here too as well, and then, you know, put it later. I think, you know, if you are planning to, you know, get started and then go try to do the contest, then I'll definitely try a more advanced hyperparameter search than just a grid search. Okay. So in this case, I'm using 7 workers, and the reason why I'm doing that is because this is going to run 1, 2, 3 times 3. Is that what it's going to run? 3 times that, I think so. And then so if I use fewer workers than the workers I have available, I'm able to actually use, well, I guess my limitation here is going to be the GPU, but I'm going to be able to basically, yeah, there you are. So there are all of those here. I'm going to be using, you know, more CPUs. So, and then in a little bit, I'm probably going to start utilizing the 2 GPUs. There it is. And then now 16. So I could even do a little bit more. I think, you know, I'm being nice to the computer. Okay. So while we do that, I'm going to switch and continue discussing now the rewards, because we're going to be training that stuff in just a minute. So somebody asked, does the agent get a reward for getting closer to the ball? Sort of. And here's the detail, right? The details are, all right, so rewards. The football agent includes 2 reward functions that can be used out of the box. So here's the key point. They can be used out of the box. That doesn't mean that you have to use that. So most of the work, if you want to you know, experiment with this, I would say is to implement your own reward function. Here's the caveat, right? So the more you add to the reward function, the faster your agent learns almost all the time. There are some kinds of reward functions that are called, and this is a paper out there by Andrew Ng when he was a student, but there is a potential-based shaping, which is a way that supposedly, well, I mean, when you are in the discrete state and action spaces, so in the simple case, if you implement that type of reward shaping, your policy is invariant. So the optimal policy for the environment that the original environment and the environment that you modify basically by adding new rewards is the same, which is really good because this means basically you're not adding bias to that. Now, in the world of deep learning, that all goes down the drain. It doesn't really matter. You have a neural network, nothing, there's no theory there helping you, okay? But the idea is still there. I want to, let's see, yeah, I want to talk about the rewards they have so that you can have an idea, an example, but I would recommend you add your own, okay? So here you have one, and then here's the other one. The first one, the scoring, corresponds to the natural reward where the team obtains a +1 when scoring the goal and a -1 when conceding one. Great, okay. The scoring reward can be hard to observe during initial stages of training, so they're explaining here why they're going to be adding additional reward, and this is a very common problem in reinforcement learning. Usually you want to say like, hey, make me $1 million, I'll give you a +1, and it's not that easy, right? So you have to usually work a little bit more to actually give it more. So one of the things in AlphaGo, AlphaZero, and all those versions, or actually I think it was AlphaZero, is actually that it was rewarded to, it didn't have much shaping. It just had a +1 for, winning the game, 0 when it tied, and then -1 for losing, right? So that is why it was a very popular, I'm going to say, accomplishment, right? Let's see. So the scoring reward can be hard to observe in each state and may require long sequences of consequent events, overcoming the defense. Yeah, so potentially strong opponent, potentially, and scoring that goes to a keeper. Okay. The second reward is shaped. And so when you see this word over here, shaped, that's what it means, is that you do have that 1 and you have the -1. But you're going to give him a little breadcrumbs to the agent. You're going to say, hey, you know what? If you do this thing, I'll give you a 0.1. If you do that, I'll give you a 0.2 and whatever. The problem with this is, well, let's read this and then I'll tell you the problem with doing this whole thing, okay? All right, so reward that specifically addresses the sparsity of scoring by encoding the domain knowledge that scoring is aided by advancing across the pitch. Okay, so it augments, well, so you see it's like, so what they're doing here is they're going to add an auxiliary contribution for moving the ball close to the opponent goals in a controlled fashion. More specifically, we divide the opponent's field in 10 checkpoints regions according to the Euclidean distance to the opponent's goal. Okay, so I guess, you have the goal there, like you have, this midfield, this is your goal, this is their goal, they do 10 things in here, and then every time that you enter, says here, the first time that the agent's team possesses the ball in each of the checkpoint regions, the agent obtains an additional reward of +1. So, +0.1, sorry. This extra reward can be added up to +1. The same as scoring the single goal. Okay, and then another caveat there, any non-collected checkpoint is also added when scoring in order to avoid penalizing agents that do not go through all checkpoints before scoring, right? So imagine that the agent shoots from here and then, scores the goal, and now all of a sudden the agent is not going to have that, right? So it's not going to have this, and this. It makes no sense, right? So really the goal is to score. So if you score even from here, it doesn't matter. I'll give you the, +2 as opposed to, only, plus point, or I guess it was 1.2, which would be not exactly what you want. The agent is always going to prefer to, drive all the way and then shoot from here, but, pros and cons. Okay. Let's see. So let's see if I don't miss anything here. Any collected rewards also when scoring, when penalizing the agents. Finally, checkpoint rewards are only given once per episode. Okay, right. So because I don't want the agents to get, in a loop, basically, you can imagine the agent going like, oh, look at that. If I go here and then, oh, go out and go back and go out and go back, and that's not the behavior that you want. So that makes sense. Now, here's my thing is, does it make this shaping? Maybe, maybe not. The problem is that often in reinforcement learning, what you want is the agent to find stuff that you cannot find. Then the more you add rewards, the more you're adding bias to the agent, right? Like, if you like soccer, you understand what I'm saying. There are some teams play the possession game, right? Pass the ball and then pass, tick, tick, tock, tack, whatever they call it, right? So passing back and passing to the side and then to the side and then control and control and control. but they end up losing the game because they're not scoring more than the opponent. Is that a good thing to do? Like, 700 passes per game, is that what we want? No. So that's kind of a caveat there, right? So when you're adding the extra reward, then you perhaps are going to be biased. Your behavior is going to be biased. It's not something that you want. So often you got to be very careful with this. The other thing that you got to be careful with is that usually shaping, in some cases, if you say, oh, +1 for moving the ball, then you're going to have different things. The agent is never going to want to shoot the ball. Like if you have, imagine this thing over here. And let's say that instead of 0.1, we're actually doing a 1, a whole 1, right? Then the agent has much more value by controlling the ball and then shooting all the way, collecting all those ones, unless what they did there, adding all of the checkpoints that they didn't, that the agent didn't go through with the goal, which it also makes sense. Now, for instance, with that reward function, the agent is always going to prefer to shoot from here. And you say, why? What are you talking about? Why would that be? They're giving the reward. Because there is such a thing as a discount factor, right? So the little thing gamma, and again, if you don't know what I'm talking about, I highly recommend you go get the book and try to read those things so you understand what's happening here. The agent is gonna say, well, it takes me so much time to go all the way here and then shoot the ball. So as opposed to me waiting all that time and discounting the value of the reward that I'm getting, because the agent is gonna be here, it would get the 0.1, 0.1, 0.1, so many steps, right? Like imagine 500 steps all the way until it gets here, and then he shoots that and he gets the +1, okay? Imagine that was 500 steps. So what is this gamma value gonna look like? Like a tiny, tiny, tiny little value, right? And then when you multiply that to calculate the value function of the initial state, the first state when the game starts, that contribution is going to be so small to that value, okay? Hopefully you're understanding what I'm saying. So if you are here and shoot from here, the shooting, I'm assuming, is much faster. So you boom, and then the ball gets there. So let's say that takes 100 steps as opposed to 500 when you're dribbling. 100 steps, then the discounted, and then you're gonna receive a 0.1 here, and then in 100 steps, a +2, right? So the value here is likely, the contribution to the value function is likely higher. And you could actually calculate these things, and if we were doing a serious thing, I would probably calculate that to make sure that I'm not going crazy. I would actually sample, make sure that my assumptions are actually correct, right? So I would actually sample the environment, see, oh, is this 500 steps or 200 steps, and how long does it take to shoot from here and here and so on. But yeah, so things to have in mind, okay? So that's the rewards. That's it. Let's flip back to the computer. Let's see. And please, if you have any questions, let me know. I'll be happy to answer. You guys still there? Yes. All right, so yeah, CRAD is the player rewarded for getting closer to the ball. So it's not rewarded for getting closer to the ball, although it could, but it's rewarded for getting the ball closer, or actually going through the opponent's field, which is, an interesting take, but, perhaps your idea of getting closer to the ball is better. I recommend in that case that you check the video, George Zek videos of, it's called Messing with Rewards, the RLDM course. By the way, I have those videos also on my YouTube channel, so just go ahead and look for that one. It's a class by Professor Charles Isbell and Michael Littman, and they discuss actually a very similar game. Actually, it was a soccer game, but not with this, but with some other simulator. But yeah. All right, so look at that. So training has finished. You can see here we have all of the different trials. All right, so each guy here, each row is a trial. And now you can see here, each trial was sampled with a different gamma. And that's because I said NP random uniform from between 0.9 to 1. Now their learning rate, as you can see, is the grid search. 0.002, here's 0.002, and 0.02. Now, it did this guy, then this guy, then this guy, and it did it 3 times because of its number of samples. Okay? I hope that makes sense, because it's important. So once you are actually playing with the environment in a little bit more depth, then, you know, I would actually do, when every night that you're done, you just like leave a lot of samples running and see what it is. What is the punishment if players take bad action? Well, it's a good question. I think, according to what I see, there is no punishment but the goals, right? So you get score on, and then you're going to get -1. Now, I did see a lower return, I should say. So I'm thinking perhaps if the opponent goes through your side of the field, perhaps you get a -0.1 when the opponent is getting a 0.1. I don't know. That would be a good thing to check. That's a good question, actually. Okay, so again, we have all the different ones, and this is the things that you care about. Here, in this case, is the reward. That's the value, then the reward max, reward mean, and episode length mean. And if we go to the tensor board, and this is when tensor board becomes a very, very helpful tool, is that you can now see your different runs, right? And then in this case is the carpal environment, and I use pretty okay values. So, you know, I would say, no, it's not really that helpful, you know, because what is the variance there? And I would, you know, likely run many, many more and much wider values. And then you would have actually here, you would have actually something that would tell you, that would inform you of which values you should be using and which ones you shouldn't. But yeah, that's the test that I wanted to show you. Okay, so once you train here with tune run, you're going to return an object that is the kind of analysis, I guess they call it. I don't know, I forget the name exactly, but you know, if I run that, you're going to see you have a few functions. So there A is going to give you the functions of this particular object. And some of the things that you have in there is the best checkpoint, the best config, the best data frame, best log there, and so on. So what I'm going to do is with that object, I'm going to get the best trial out of the trials that are in there. And I'm going to get the max episode mean. That's the criteria that I'm going to use to get the best trial. And then I'm going to use that best trial to get the best checkpoint of that best trial. So I'm going to get the best checkpoint with the same criteria. And I'm sure that there should be some function that does that in one step for you, but I didn't find it, didn't have much time. So here is the checkpoint. Look at that. So checkpoint 9, this is the TensorFlow checkpoint. This is the policy. So basically what we're saying here is that these are the weights of the policy that got the highest reward. So this is what you want to use to compete, in other words. So in this case, you know, I got that. And then what I'm doing is now config, PPO, default config, copy. What I'm doing here is I'm grabbing a config, a PPO config. I'm saying don't use any workers to make sure that I'm just going to roll out. I'm just going to use the policy to ask the policy what action should I use given this particular state, and in reality, this particular observation. So, you know, here, observation as opposed to state. But then I run this guy. And here you can see the episodes coming back, right? The return is 200, 200, 200, 200. So I'm basically saying that the agent is doing a perfect job at what it's supposed to do. In this case, is the carpal. I can actually, you know, run this command here to see my agent perform in the carpal environment and now, voila, you're going to have there the agent. So the agent is controlling that in a perfect way. So that's it. Great. Cool. Okay. So now we know how to do that with a carpal. We know the Google football environment. We know our lib. Now we pull these things together. Okay. And then we're going to train the PPO agent, but to solve this. So here, in this case, I want to bring to your attention that sometimes the number of policies and the number of agents are two different things. You could have a single policy controlling all of your agents, and that policy would be, using observations from all of the different agents and not combined in a single way, but more like, you can imagine that you're moving the agent on different, moving the agent to different players and then controlling each player that way. Okay. And then so those are two different things, and it's up to you to kind of, play around with that. Here I'm doing the simple case, which is, one policy, and this is a single agent case. Here, this is a way when you need to register an environment with our live so that you can use it. So I register it. Here, this little hack here is that, sometimes you want to delete the environment. If you replay this cell multiple times, you would actually have an issue because the environment has not been deleted. So just add it there. So delete it if it exists. Otherwise, don't complain. And if it didn't exist, just don't complain. I don't care. So here you can see I'm passing. This is a helper function. You can see the helper function in here and play with it. This is a class. Again, half credit to the Google folks because they provided most of this interface. I would spend more time polishing it if you want to continue working on it. Here I get the observation space and the action space from the perspective of a single agent, and then I generate the policies like so. These are policies that are going to be later. If you're doing a multi-agent training, you're going to be having to use this if you have multiple policies. In this case, it's a single policy, so I'm not getting into that complexity so far. But there you see it. We confirm that the action space is that, the observation space is that. Then you have those policies. You can see here is a single policy, so it's not a big deal. Policy IDs are those. Right now I'm clearing the logs so that these guys go away because it's not a carpal anymore. You can also leave it. They are going to be organized by the experiment name, but I'd rather not complicate those things. And that's it. So here's one thing. This training takes time. And I'm obviously not going to be sitting here for 2 hours waiting for the training to complete. I will, however, switch to a Q&A after this. But I'm only going to do, let's see, like 250,000 steps. So that would take probably 10, 15 minutes or so. And then I'm going to wrap up. Now here, I would say, train, once we're done, go ahead and train with 5 million by yourself, right? It's not a big deal. You can see here that the episode mean, now I lower it to 2. You can play with that. I also made the gamma a fixed value. Learning rate is there. It's a single sample. You can do a grid search the way that I show over there. You can see here that I'm using 30 workers. You're going to have to lower that number, of course. It's too much, or unless you have, 32 like I do. But other than that, these are other things that you want to kind of become familiar with. Checkpoint frequency is the number of iterations. So every 10 iterations, training iterations, whatever that means. Again, that's a little harder to understand, but that's okay. Every 10 training iterations, I'm going to create a checkpoint, okay? Additionally, I'm going to create a checkpoint at the end, regardless if it ended up at exactly a 10 or at the 3rd iteration. It doesn't matter. I'm going to create that final checkpoint when this thing gets hit, which is either this guy or this guy, right? The number, so I'm gonna keep 3 checkpoints of those guys, and I'm gonna use the episode reward mean as a score attribute. Basically, RLib is gonna do it for me. It's gonna look at the highest episode reward mean checkpoints, and is gonna keep the highest 3 at any given time, right? So that's actually super useful because, you know, all you need to do is train this puppy and yeah, it's gonna start showing in here in any second. Let's see the resource. So CPU being utilized, RAMs kicking in there, and the disk. Let's see. Okay. It's coming, it's coming. There it is. And that's it, it's running. So you can see here, so far it's not, there's not a full episode. So when you see the 9 in there, usually means that it hasn't completed a single one and already collected a bunch of data, but it's not able to get the statistics because of the size. But in any second, this thing becomes just regular numbers. And then the end of the notebook, you're gonna see that I basically customize everything else so that you can do the same thing that I did with the carpool environment, but with this other environment. And it's a little bit different, but you know, the functions are in there. Again, you're gonna see here, you're gonna get the checkpoint of that guy. So the important thing is that this object over here is gonna contain all that information. You're gonna get the checkpoint. Then you're gonna load the checkpoint into a policy, into an agent here, PPO trainer. You load that guy, and then you create the policy, and then you have a little function that is like, you know, give me the action for this particular state. Then here I'm creating a single instance, so a single agent of that environment, just so that I can, a single agent, how do I say it? Like an independent environment so that I can run it one step at a time. Reset in there just to see what the information comes. Look at this, this actually has a key value pair. And the introduction to multi-agent RL, and again, you know, I'm way over my time, but I'm gonna say that when you're doing a multi-agent RL, I recommend you look at RLib's interface. So OpenAI created that OpenAI Gym interface for single agent. But when you have multiple agents, then you know a problem shows up. Like, okay, what is the observation? What is the reward? Like, how do I know which reward goes to which agent, and so on? So RLib came up with another interface, which is pretty straightforward, and also I guess other folks also came up with the same interface anyway. But what people use for multi-agent is a dictionary, as opposed to, let me put it here. Let me go back to this guy. Okay, you can see that. So remember the agent. You can imagine here now we're gonna have the agent, agent A1, agent 2, agent 3, and then you have a single environment. And environment wants to talk to this guy and give him something, and wants to receive something from that guy as well. So, okay, wants to receive the action and know that that is the action and this. But this system of doing it independently like this is a little cumbersome because you want you want it to be synchronized, right? So what people do often is, you can imagine something like this. Imagine these are like the policies. These guys over here are the policies, and then you have here like an actual, like a main agent. Not quite. I'm hopeful this is probably not the best way to explain this, but let me proceed and then I'll try to clarify it. So you can have here the environment, and what's going to happen is the environment and the agent now are going to be communicating through dictionaries, right? So, a dictionary is going to have a key, agent 1, and then something, right? And then agent 2, and then something, and so on, right? So now this guy is going to pass the environment the key value pair that contains the actions for each of the agents that are available in there. Now, the advanced multi-agent stuff, agents can come in and come out at any given time. In reality, you can think of agents showing up like, let's say, let's imagine that this soccer game has substitutions, right? And then a new agent comes in the 60th minute, right? So you want to be able to reflect that, and then agents can come in and out. Now, in this particular environment, I don't think that they have that available. I highly doubt it. But that would be an interesting thing if they had that. But I don't think we need to worry about that for this environment. Now, when you return stuff, instead of returning observations, rewards, dones, and infos, each of these guys are going to be a key value pair that is going to have the key is going to be the agent that should get that observation, and the value is going to be the actual observation that the agent should get. And then here the same with the reward, and then the same with the done, and the same with the info. Every single little thing has the same thing, the same kind of interface. So this guy here in the middle is going to say, oh, never mind, you go ahead and let me give you your stuff, let me give you your stuff, and then give me your stuff, I accumulate, and then send it to the environment, and so on. So that is how the multi-agent is done. And that's why you see the format that I have in there. Let me flip back again. The format, excuse me, the format that I have in here is agent 0, and then that is the observation. Okay, and then later you're gonna see here that I'm actually doing now, agent 0, I need to actually now index that with the agent 0. And then the done all means that when every agent is done, because you know that the agents can be, so if you imagine that you have 11 players and they get substituted at the 60th minute, then a few agents are going to be done, but not all of the agents are going to be done. So the the done _ all is going to be telling every single agent, you guys are done. Like, this is done for real type of thing. So that is the interface. I kind of explain it to you now with all that. But if you run the code here, go down the line, you're basically going to go down to this, and you're going to see your agent doing something a little bit better than, than what it was doing before. Now, it's not perfect. This one is actually, I train it for very little. But, and I haven't tuned the hyperparameters of this particular environment. And I don't like that that the episode reward mean is actually going down. But no, when I run it for 500,000, 500,000, I think I run it for 500,000, it was starting to go up. So the value should get you going, but obviously you can customize it and make it better. Now, I'll give you a few tips here that what you can try. An agent such as the PPO agent has multiple different knobs that you can tune. So go ahead and take a look at it. Actually, this is what I recommend. You do PPO that pod. Let's see. This page over here is what's going to give you the information of what the agent really does, or in what you can actually fine tune. You look, use critic true, use generalized advantage estimation, and you would have to go read the paper here to get more information. Lambda, KL coefficient. These are kind of more training hyperparameters, but this is, so the training iteration depends on these values, for instance. You have the shuffle stuff, the learning rate, share values, all of this stuff. And in my book, I talk about these things, okay? So my book tries, I try to explain all of these things, actually allow you to implement it. Again, obviously, sorry, commercial time, right? Go ahead and get it, Grokking Deep Reinforcement Learning. So chapter 12 actually talks about PPO, this particular algorithm. So I highly recommend that if you're going to be using this, go here. Otherwise, if you want to use some other algorithm, I know a lot of people are familiar with other algorithms such as DQN, whatever, go there. Go to the DQN and then open a DQN.py. And that's it. You're going to be able to, look at their values, their stuff, the buffer size, the prioritized replay buffer, the target network frequency update. I also teach that in my book, chapter perhaps 10, I don't know, 10, 9? I think it's 8, 9, 10, all of those. So the DQN chapters. Highly recommend you go there. Oh, let me see. Okay, we got questions. What's the punishment? You said that. Are the agents, they didn't share the weight like DDPG A2C of the model when it has been configured as one policy multi-agents? Yes. So there are 2 layers there, right? So you have workers, the rollout workers, and those guys are, share in a more in a tightly fashion. They're all synchronized, and then the updates go like that, and so on. When you're doing, I guess it's called independent. So it's a single agent controlling all different players of the game, then you can also share observations. Now, the only caveat that I'm gonna mention there is that you can think about this, right? So off-policy learning may be an issue here, okay? And usually non-stationary is also gonna be an issue, but if you have a replay buffer, something like a DQN or a DDPG actually that you're saying in there, but though this environment has a discrete action space, so I would probably use a DQN or A2C with a policy that outputs discrete actions. Then if it is off policy, then you can use data from basically any agent, and it would actually be okay learning with that. If you're going to be using a PPO, you may have problems there. Now, RLib already works that out for you, and then when you do a training like this, like a multiple policy, then they fix some of that stuff for you with the observations. Okay, so it's like sharing, yes. And then so will the same observation be stored multiple times equal to the number of agents in the replay buffer? From the perspective of that other agent. So in the case that the agents, and I don't think this is the case, but if the agents look at the game as the whole frame, then yes, it's going to be exactly the same in the replay buffer, which is probably you're intuitively asking that's why you're asking the question. Not a good idea. Then yes, I would probably fix that. But I think the 115 vector should probably be different for every player. So those are not going to be identical, right? It's not the same observation. It's going to be this from the same time step of the simulation, but from the perspective of each of those players, right? You have 11 players. It's going to be from the perspective of the goalkeeper, what is happening, from the perspective of the striker, what is happening, and so on. Hope that makes sense. All right, so let's see how the training is going. Okay, we're going up. Finally, I was like, oh no, look at that. That only happens on streams, right? No, it starts going up, and then like around the million, then starts going all the way up. And you can see here is the max is actually going sharp up, which that's another thing that you can do is like, if the max goes up like this, and then the agent gets stuck basically to that kind of max, something good is happening. Okay, so then you can expect the mean to start going up, 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 depending on what the minimum is, right? So here the minimum is the other thing that you want to look into. Now, there are many more things that we just scratched the surface, guys. I mean, super. I'm happy that that we did all this stuff. Oh, look at me! It's my face on my face. Kind of happy that we did all this stuff. I mean, it's a lot to go through. I didn't change much, but I probably won't push my changes. I don't think I change anything really important. Let's see, or should I? I'm just gonna do it in case. So I'm gonna push all of the changes I made this run, and feel free to pull the new information and get up to speed. I think this should get you started, should get you going. When you finish this, you're gonna see that your agent learns to play 1v1. And in this case, it's 1v scripted. It's not really the one on the other side, but it's a one learns to defeat that other player. I encourage you, try to continue exploring that path. I think what I'm providing here should give you that, that bump, bootstrap you and get you somewhere. Again, final hook, Grokking Deep Reinforcement Learning. The book is going to be available on Amazon November the 10th. It is already available in Manning, so you feel free to go there, and there's going to be a discount somewhere. I hope that they actually put the discount somewhere. If they haven't, then I'm sure it will show up at one time, or send me a tweet, tag me on a Twitter or a tweet message, and I'll try to get a discount code for you. But I highly recommend it. The real copy is again just available. Other than that, again, my Twitter, just follow me on Twitter, MIMORALEA. I'll be releasing more content in the upcoming weeks. And if you have any questions, just feel free to reach out. I think, yes, Lahad. Okay, that's the link. That's probably one final thing that I probably, let me do that actually, because this is actually what motivated me to do this environment. Thanks for sharing. So I'm going to share my screen then again to just go over that real quick. All right, so this is the competition that is currently going, right? So it says 24 days to go, 17 days until merger deadline, whatever that is. $6,000 prize money. I mean, really cool stuff, right? And then it's kind of sponsored, I guess, by Manchester City. So go ahead and check that out. Now, this is a series. I did a 1v1. You need to submit 5 agents to the competition. Now, I did all the way to 5v5. So, think about it. It's there. I give you a little bootstrap, right? So just go ahead and do it. I probably won't compete, but if you have any questions, let me know. Look at that. So really, really interesting. You got some money in there that should definitely be of interest. So again, my Twitter, again, is this guy over here, that over there. And then very, very soon, my YouTube channel, I guess is channel Agent Whisper or something. I don't know. I need to get up to speed with that. Agent. Did I get it? No. Okay. I'll tweet it. Very, very soon. I'm gonna have I'll start posting a bunch of videos, and I think it will be nice that you guys follow along. I think it's gonna be fun. Oh, let me see. There. All right. So, do you have a Discord channel? I do not. I actually joined they have a Discord server that is reinforcement learning. I joined that recently, and I'm there. There's a lot of good stuff going on over there. I highly recommend that. Send me a tweet if you want the link. I'm honestly, and I'm sorry, I'm not a pro on Discord. I only found out kind of recently, I guess, not too long ago, a couple years back, but I haven't used them much. And then recently, I found this reinforcement learning I guess they call it server, that has a bunch of channels, right? And you know, I'm hanging out in there. So if that's what you're asking, I hang out in there often. And will you post this video on your YouTube channel? I think I'm gonna leave this video here. I'll probably ask Manning if they let me, you know, cross post, but I know that Manning actually posts this anyway. So I think I'm gonna start posting new stuff on my YouTube channel and more condensed, obviously. We'll do 1-2 hours at one point, but for the most part, it's gonna be 10-minute videos. Like, I'm gonna explain to you just a very specific algorithm and, you know, a very specific problem and so on. I don't wanna, you know, I don't want you guys to have to deal with my moments of thinking, right? How do I say this? I'd rather you guys to get the information straight when you want it, and sometimes this format is also good. But yeah, that's it. I hope you like it, guys, and yeah, support the book. You know, Twitter. I'll tweet my my YouTube channel soon, and then I'll start posting, and I hope you get involved. All right. Thank you all. Thank you so much.